Good evening, chemists. So let's get started here. We left off talking about some properties relating to atom size. So the idea here is we have three criteria we're kind of keeping in our back pocket. N value of valence electrons. We're looking at Z effective of those valence electrons, and we're looking at any extra electron repulsion that may be present if it's an ion, if like a cation or anion is present. And so with those three criteria, it helps us predict radius of elements or atoms. It helps us determine ionization energy of our atoms. So this is the energy to remove an electron, to rip an attracted electron from its nucleus, oftentimes held there by its effective nuclear charge. And so the idea here is that, we can predict our charges of different metals based upon where they are, their group number. So like sodium only has one valence electron. It usually only forms a +1 cation because only one electron is easy to remove. Magnesium has two fairly low ionization energies before there's a huge jump because we start taking electrons from inner core electrons. So basically locating that big jump is how you dictate, okay, where is your inner shell? How many of those electrons are how many of those electrons are valence electrons? So we left off looking at some of these questions here, common exam questions relating to that idea. I showed this graph, which is showing different ionization energies for an element. And I ask you what second row element would possess these ionization energies. So each of these dots is an energy relating to removing an electron. So you might look at this and be like, oh, I see 1, 2, 3, 4, 5, 6 data points. That's 6 valence electrons. This has 6 valence electrons. But is that what this graph is trying to say? No, it's saying that there are 4 electrons that are easy to remove, and then the next 2 are very hard. And so the idea here is that, okay, 4 electrons easy to remove, that sounds like a valence electron. So to me, this graph is showing, hey, there are 4 valence electrons here. And so ask yourself, what element has 4 valence electrons and happens to be an N equals 2 element? It would be carbon. Yeah, so this would be the ionization, this could be the ionization energies for carbon. And to note here, see how all of the successive ionization energies, they always go up. You don't see like a dip down to like, oh, the first ionization, the first electron's easy to remove, the second one's harder, the third one, oh, is a little bit easier. You don't see that. It goes up, and then you see a huge jump, which indicates your inner shell. All right, so that's the second question. Let's look at the first question now. All right, what is the equation that describes the third ionization energy of aluminum? So my trick is for ionization energy, it's yes, energy to remove an electron, but the detail is it's that you're removing 1 electron at a time. So when I say third ionization energy, I don't mean directly make a aluminum 3+ cation. I don't mean that. I mean, we want to take electrons off 1 at a time. So oftentimes I think, if I say, I tried to make mistakes that I think students would make. So here, the third ionization of aluminum, you might think, oh, we want to make aluminum 3+ from aluminum. Like that kind of makes sense, right? But this first one is incorrect because, well, one is this charge balanced? Are the reactants and products charge balanced? No, they're not. So it can't be A because it's not a balanced equation. Well, what if I balance it? What if I, put the aluminum 3+ and 3 electrons on? This is balanced, but is this the third ionization energy? No, because in the reaction in B, I ripped off all 3 electrons at the same time. So B is not correct either. So from process of elimination, the correct answer is C, but let's think about how we can get to it. The idea is when we stack all of our successive ionization energies, we take the product in the previous one and make it the reactant in the first one, or in the next one. So I think, a good thing to do here would be to write all of the ionization energies just for practice here. So if we write the first ionization energy of aluminum, we take a neutral aluminum, we rip off an electron. What is the product if we rip off an electron off of a neutral aluminum? Al, what charge? +1, yes, and you see how that's charge balanced on the product side. All right, so that's our product. So that's the first ionization energy. So the second ionization energy is you take the product in the previous step and you make it the reactant in the next step. So the second ionization energy is you take aluminum plus, you rip off an electron, and that's how you get aluminum 2+. And you see how it's like that reaction alone is still charge balanced. Both sides have a total charge of +1, right? And then to get the third, I hope you can see now we can make the third ionization energy by taking the product in the previous step, right? So this would be the third ionization energy. You take aluminum 2+, and you rip off an electron, and that's how you get aluminum 3+. So that would be our answer. So that's the long way to get the answer. Right, but I want to show you how that is, that we're taking off an electron one at a time. Of these three equations, which one will require the most energy? Which one will require the most energy? First, second, or third, or do we not know? Third? Third is correct. Third is correct, because the idea here is in the third ionization energy, we're ripping a negative electron off of a +2 aluminum. So we're separating some things that are already attracted towards one another because we have a negative electron and a +2 aluminum. There's like a lot of attraction there. Versus like the first ionization energy, we have a neutral aluminum, so it's a little bit easier. So yeah, once things start to become more charged, right, that it's harder to remove those electrons. Okay, so there's that question. Let me draw some graphs. And you tell me which one represents the ionization energies of aluminum. Wait. Okay, there's that one, and then I want to do... Okay, so I have three graphs. Let's call them A, B, C, and D. A, B, C, and D. Which graph? Okay, so this is energy, all right, ionization energy. And then the x-axis is just number of electrons, so taking them off one at a time. So which one of these graphs would properly represent the energies of the ionization energies of aluminum? A, B, C, or D? D, yes, D. What's the thing that you're looking for here in D? You're looking for three small lines or small energies and then a big jump. Where does that 3 come from? Why is 3 relevant here? 3 valence electrons, it's in group 3A. Well, what about C? C has 3 short lines and then the 4th and 5th are tall. Why not that one? Yeah, it's going down. It looks like here that the first ionization energy is the hardest, and then the third one is the easiest. That doesn't happen, all right? Because the idea is when another reason why ionization energy increases as we remove more electrons, cations are always smaller, right? So once we have smaller ions, isn't it harder to remove electrons anyway? Yeah, so that's why it always gets harder. And so the big jump is how you figure out where our inner core electrons are. All right, so that's another way to ask the question. All right, so third one here. Let's consider these 3 elements: sodium, calcium, and sulfur. All right, and so I have those labeled here on my, my nifty periodic table. So there's sodium, calcium, and sulfur. So we want to figure out which one has the largest first ionization energy. And so I gave you a hint here. The idea is we're moving an electron, so we want to look at size. So N value, this shouldn't say size, it should say Z effective. Sorry about that. So the idea is the more attracted the valence electron is on your atom, the harder it is it's going to remove. So we're looking for largest ionization energy. So we're looking for a small atom with a highly charged Z effective. So which atom is that? Which element is that? Sulfur, right? Yes, because the idea here is calcium is N equals 4, so it's the biggest. So the idea is if, you have a bunch of, electrons around you, the further away they are from the nucleus, the easier it is to pick them up, versus if they're really close to the nucleus, it's harder. So we want to be looking for smaller atoms, so sodium and sulfur. And then of those, sodium, sulfur, because they're in the same N, we look at Z effective. So sodium has a +1 charge on valence electrons versus sulfur has a +6. So those valence electrons on sulfur are attracted much more. So it's going to cost me more energy to rip them off. All right. So that's the first ionization energy. Now, let's look at, okay, which of these, the same ones, has the largest second ionization energy? So energy to remove the second electron. Which one do we think it is? Which one? Sodium. Why do we think sodium? There's only one valence electron. Yeah, so the correct answer here is sodium, because sodium only has one valence electron, so the first one's going to be fairly easy, but the second one's going to have a huge jump. Now we're taking inner core electrons, versus for calcium and sulfur, the electrons we remove there, they're all valence, so they're going to be relatively easy. Cool? Okay, so that's the types of questions we can ask for ionization energy. Energy to remove an electron. Electrons that are attracted and electrons that are close to the nucleus are hard to remove. Now let's talk about the last property, and it's probably the hardest one, because in ionization energy, energy to remove an electron, it's always endothermic. It's always a positive number. But for electron affinity, sometimes it's positive, sometimes it's negative. And the thing here is, oftentimes if you've taken chemistry before, all right, okay, I remember, I guess my chemistry background wasn't very good in high school, but my high school teacher, I think they taught that electron affinity and electronegativity were the same thing, and it messed me up for a very long time, all right? So I'm here to tell you that if you think about electron affinity as the same trend as electronegativity, that's not right. So just listen up here. I'll try to teach it to you the correct way here. So electron affinity is literally not the opposite, but very similar to ionization energy, where it's energy associated with, adding an electron. When we did ionization energy, we removed electrons to make cations, but with electron affinity, we're adding electrons to make what kind of ion? An anion. So we're making negatively charged things. So we're putting electrons on atoms to make an overall negative charge. So sometimes this process is exothermic. All right, so like in the first example here for chlorine. So see here, chlorine, we're taking a chlorine atom, we're adding an electron, and then we're making a Cl minus anion. This process, this reaction is exothermic. This process is exothermic. You can see it from its negative value for its enthalpy. Versus if we try to add an electron on argon, we see that it's actually a positive number. It's endothermic. It's not super favorable to add an electron to argon. So we want to focus on these exothermic reactions, the reactions where it is favorable to put that electron on. Where that energy comes from is the attraction that this electron has to the valence shell of that atom. So we want to be thinking about Z effective here. That in the valence shell, what's the Z effective of a valence electron on chlorine? What's the Z effective? What's the quick and dirty way to do it? It's group number. So it's +7. So all those valence electrons on chlorine feel a +7 attraction to the nucleus. So think about it. If we add an electron to that same valence shell, doesn't that added electron also feel a +7 attraction? So that's where this exothermic energy is coming from, that this electron is actually attracted to the nucleus because of Z effective. So this in the red box, because I think it's important, because this one's harder to envision, all right? That the greater the attraction of your atom and that added electron, the more exothermic electron affinity, or the more favorable electron affinity will be. So a big negative value is what we call a favorable electron affinity. And again, common mistake, electron affinity is not the same as electronegativity. This affinity idea, it's an energy term. Electron affinity is an energy term, just like ionization energy. Electronegativity doesn't have units. That's what messed me up for a long time, right? So the idea is high attractions, more energy given off. We can also come back to our favorite thing here, electrostatic attractions and potential energy, and think about, okay, more Z effective, more negative electron affinity. Or another way we can have a really favorable ionization or electron affinity is if we bring that added electron close to the nucleus. That's another way we can get more energy back. So the general trends that we see is that if the size of your atom that you're adding your electron to is small, you have a large electron affinity. All right, a large favorable, so a large negative value of electron affinity. We're typically referencing the negative value, the exothermic value. So as size decreases, electron affinity is more negative, that the magnitude becomes bigger. Also, as Z effective increases, so higher attractions of that electron, you also get a negative electron affinity here. And so here are some values for different electron affinities. So we see that some nonmetals over here have very low negative electron affinities. It's very favorable to add electrons to nonmetals. We kind of already talked about that in chapter 2, but this is why. It's because we get a lot of energy back when we put an extra electron on chlorine. We get a lot of energy back. That's favorable. Versus, there are some instances here, noble gases, they don't really accept electrons very well, that it's not super favorable. So we have positive values within there. There's a couple exceptions here that you might see, that alkaline earth metals, so you see here for group 2A, they're actually slightly positive numbers or 0, and it's just because when we add an electron, that added electron goes into a new P subshell, and that's not super favorable, so they're just slightly positive, so it's not very favorable. Also group 5A, so the idea here is that 5A elements have 3 unpaired electrons all spinning the same direction, and so if we add an electron, where's it most likely that electron's going to go? It's going to be spin down, all right? And because we're basically adding this new spin, it's not super favorable to make an N minus either. So this is not favorable, and you can see that from the graph here, that the electron affinity of nitrogen is actually slightly positive. And probably the biggest exception here is you would think that because fluorine is the smallest atom, other than like helium, fluorine's the smallest atom here, you would think, oh, fluorine's really small, it has a really high Z effective, putting an electron on should be really exothermic. It should have the most negative large number, but that's not what you see. You actually see chlorine is the lowest, the most negative, most exothermic electron affinity. And the reason is that fluorine is already so small. Just imagine, fluorine's really, really small. We are trying to shove 8 valence electrons in a really small space. When 8 electrons are in a small space, electrons are negatively charged, what kind of force is going on there? Repulsions, yes. So when you're putting those many electrons in a small space, there's a little bit of repulsion. And so that's why it's actually just less favorable than predicted for fluorine when you add that electron. Versus chlorine is bigger and can actually accommodate all those added electrons. So it's actually a little bit more favorable for chlorine. So that's a small detail. So the idea here is once you make add an electron, all right? So when we add an electron to oxygen, we make O minus, all right? So just like ionization energy, where we can remove electrons one at a time, we can also add electrons one at a time. So this, what I just wrote, is the first electron affinity of oxygen. But just imagine, what do you think the second electron affinity of oxygen is? All we do is we add another electron. So what's our product here? O2 minus, yes. So this last idea here is that, so this reaction, the first one I wrote, this is a favorable reaction. It's a negative number. You can look at it on this graph here. But the second reaction that I wrote, this one, is actually endothermic. It's a positive value, all right, that it's always unfavorable to add that second electron, always. But because let's think about it. The same idea here. I have a negative oxygen and a negative electron, and I try to shove them together. What kind of force am I acting upon there? Repulsion again, all right, because our oxygen is already negatively charged, so trying to add another electron is always going to be unfavorable. So that's why this last exception here, all right, the last detail here, second electron affinities and thirds and fourths, they're always unfavorable. They'll always be positive. And that's what I mean that electron affinity is just a little bit tougher to wrap our head around. Because sometimes it's positive, sometimes it's negative. So let's do some practice here. So what I had in the red box is written here also. So really large negative electron affinities means that the added electron is highly attracted or it's close to the nucleus. So keep those things in mind and your potential energy equation will help you get there. So we are gonna look of these pairs, look for the larger magnitude of electron affinity. So we're looking for which atom is it more favorable to add an electron. So let's look at lithium and sodium. Basically, I wanna be looking at our three criteria again, N, Z effective, electron repulsion. And so kind of locate where these are on the periodic table, see what they have in common, what's different, and hopefully you'll see the trend there. So we see lithium and sodium. To me, I see that they're in the same group, so therefore their Z effectives are the same, but what is different? Their N's are different. So of these, since their Z effectives are different, then their Q1, Q2, their attractions are the same, all right? But the idea is the one that's more favorable will be the example where we can bring that electron closer to the nucleus. So in which atom can we bring the electron closer to the nucleus? Lithium, because it's smaller. Where the electron goes will be in the valence shell that's smaller. And so in this case, it's lithium, right? Because lithium is N equals 2? Yeah, okay. All right, so the reason is N. All right, aluminum and silicon. So we look at that, I see, okay, no, they're in the same N, but how do they differ? Z effective. So the idea here is, okay, they both have the same N, but we can inspect Z effective is +3 for aluminum, +4 for silicon. So if you're just a dumb little electron floating around, are you more attracted to +3 or +4? +4. So in that case, you will give off more energy. It'll be more favorable for you to fly towards your +4 because there's more attraction there. All right, so it's silicon. So the reason is Z effective. Good? Okay. All right, the next one, chlorine and chloride. Which is more favorable to add an electron? Remember, electrons are negatively charged. Don't think about it too hard. Okay, just use your monkey brain. No, yeah, chlorine is going to be more favorable because chloride is already negatively charged. You're trying to shove two negatively charged things next to one another. All right, and so the reasoning here is the extra electron repulsion that is from the chloride. That's why. Cool? All right, next one. Which one's more favorable? Calcium or calcium 2+? 2+, yeah, again, just turn on your monkey brain. If you were just an electron trying to go where you're most attracted, it's going to be the thing that's +2. All right, and that means you'll give off more energy when you attach to a +2. All right, next one. Iron 2+ and iron 3+. 3+, very good. So all of those, like last two, are all kind of for the same reason. Good? All right, because there's higher charge there, right? More attraction there. Okay, that is electron affinity. So that's energy associated with adding electrons to form typically anions here. So With all of that, we get to, okay, electron configurations of ions. We already did electron configurations of neutral atoms in chapter 6. So the idea here of, okay, we can actually write the electron configuration of ions, and I think it really bridges all the ideas together. We make cations by removing electrons. That's related to ionization energy. We always remove the electrons that are easiest to remove first. Also, in that same vein, electron affinity, we're adding electrons. We want to put electrons in the space that gives us the most energy back. Typically, it's the valence shell. And so with those ideas, we can add or remove electrons to make the specific ions that we want. And I think it kind of recaps from chapter 2 here that in chapter 2, I told you, okay, if we look at, you could predict the charge of nonmetals by its group number, where I say, what is it? Group number -8 is the charge. So fluorine as a ion, fluoride, is always -1. Oxygen as a anion is always -2. And I just told you to memorize it. I don't know if you ever asked why. And it's because of these ideas, that it's most favorable for an oxygen to add 2 electrons into its valence shell. Because of electron affinity, it's most likely, potassium will lose 1 electron because of its 1 low ionization energy. So all of these things come together. So let's think about it, adding electrons. So in this example, here's my neutral fluorine. I want to add an electron. Where is that electron in fluorine going to go in order to make fluoride? Where is it most likely going to go? It's going to go into that, there's 1 more seat left in that 2p subshell. So basically, I'm going to rewrite all of those orbitals, and it'll just end 2p6. We just add 1 electron. That's the next available place. That's putting an electron there will give me the most energy out in terms of electron affinity. So same thing with sulfur here. If we want to make sulfide, we're going to actually add 2 electrons. And so again, you think to yourself, where's it most likely to add those 2 electrons? It's going to be the 2 empty seats that are left in that 2p subshell. So then the end here of your electron configuration would be 3p6. I don't feel like writing it all. Okay. Good. So those are anions, where we want to put electrons in the most available, the next available seat, and that seat is dictated by electron affinity, right? The energy term. It's most energetically favorable to put it there. All right. So what about making cations? So if you recall, for our main group cations, like groups 1 and 2, I told you to just memorize. Metals form cations. Those charges are equal to their group number. But then some weird stuff happens with transition metals. So we'll talk about all of that and why it's relevant. It all has to do with ionization energy when we make cations. So the first one here, why is it cation charge equals group number? Well, it has to do with valence electrons and the low ionization energy. Kind of the idea here is, okay, now we're removing electrons to make cation, so we want to subtract an electron. I think it's pretty obvious what electron we're going to remove. There's only 1 valence electron to remove, all right? So when we make K+, all we get is argon, an argon shell. And so since we get that argon shell, if I try to remove another electron, is that going to be a low ionization, a second ionization energy, or a really big one? It's going to be a real big one, because now we have a really stable noble gas configuration. So if it's a really high energy, is it likely that it'll happen? No, that potassium, you won't find a potassium 2+. And so this is why we can, make statements like potassium as an ion will always be +1. We can say that from an energy point of view. All right, so let's keep going. So I hope you can see magnesium. In chapter 2, you just memorized magnesium loses 2 electrons to form a +2 cation. So hopefully you can see what 2 electrons will be lost. It's going to be those 2 3s electrons. So then we're just left with neon there. All right, so those ones are easy enough. Okay, so what you're seeing is we're just losing valence electrons because those have low ionization energies. Now let's look at some weird ones here. All right, so gallium is one of our variable charge metals. All right, if we're writing a name, sometimes we might say gallium-1 chloride or gallium-3 chloride, where the 1 or the 3 indicates the charge of that metal. And so I want to show you why that happens, all right? That if we think about forming gallium to gallium plus, we only lose 1 electron, right? So looking at the electron configuration, what electron's most likely to be lost, to just lose 1 electron? Just that 4p electron. So if we rewrite gallium plus here, we would be left with argon, 4s2, 3d10, and that would give me gallium plus, all right? But the idea here is, did I remove all the valence electrons? No, I didn't. There's still 2 more, so that's where gallium 3 plus comes into play. That's why the idea that gallium plus and 3 plus exist, depending on the energy available in the system, you know, if there's enough energy to remove all 3 electrons, then that'll happen. But if there's only enough energy to remove 1 electron, then you'll see gallium plus. So the idea here for this next one, where are the electrons going to be removed to make gallium 3 plus? It's those last 4s electrons. So then what's left is just argon 3d10. All right. And so very similar, you know, gallium, argon 3d10. Those 3d10 electrons, they're all paired up, 10 of them. It's really stable, so really large amount of energy is required to pick those 10 off because they're all paired. So you're not likely to lose more electrons. So you see how gallium can form +2 and +3. Okay, all right. So let's do the weird ones. Okay, so you know, when we learned about naming and variable cation charges, you just kind of believed me. But this is why we see variable charged cations, especially with the transition metals, because we often can remove, you know, a variable number of valence electrons depending on what orbitals they originate from. So hopefully you can see here, you know, the most likely place to make silver a cation would be that 5s electron. So we're just left with krypton 4d10. If you remember, silver is a anomalous electron configuration. Silver is also one of our fixed charge cations. Silver only exists as silver plus. Only as silver plus. And I hope you can see why, because once we remove 1 electron, is there really any low energy electrons that, or like low ionization energy electrons that we can remove? No, everything's filled, everything's, you know, good, that it's not likely we'll remove more. Or here with zinc. Zinc also was one of our fixed charge cations. Remember the 3? It was aluminum, zinc, and silver. Those were the 3 fixed charged. Zinc, for the same reason, only forms zinc 2 plus because what electrons is it going to lose? Those 4s electrons. So then you're just left with argon 3d10. And again, for the same reason, those d electrons aren't going to be lost. It's too much energy. Okay, so those are like our fixed charged transition metals. Now let's look at the variable charged ones. Hopefully you can see, you know, some commonalities come here. So iron has 2 common oxidation states, +2 and +3. So based upon that and the electron configuration of the neutral iron that I've shown you here, what 2 electrons will you lose to form iron 2 plus? What 2 electrons probably? Those 4s electrons, they're the highest in energy, it's n equals 4, so those are the ones we're going to lose. So iron 2 plus, we're going to axe those 4s electrons, so what's left is just argon 3d6, right? Iron 2 plus isn't super prevalent, it's not super common. Iron 3 plus, on the other hand, is. It's the most common form of ionic iron. So we need to lose 1 more electron. Like we already removed 2, let's get the 3rd one to make iron 3 plus. Where's the only available electron? The D. Yeah, so instead of 3d6, it's now going to be 3d5. Yes, so we're going to remove 1 more electron. Okay, and so this is going to be argon 3d5. Is there anything special about 3d5? Let's draw it. Let's draw it. Okay, so I want to put 5 electrons in that d orbital, the boxes, right? And how am I going to fill those electrons? Yeah, all singly. So 1, 2, 3, 4, 5. All right, so all of the electrons, this is a half-filled d subshell where it's unusually more stable than other arrangements of electrons. So this is unusually stable. So iron 3+ is actually, again, the most common form of iron ion because of this stability, extra enhanced stability that's given from a half-filled d subshell. All right, so there we go. And so it stops right there because the idea, if this is really stable, it's going to cost me a lot of energy to remove more electrons. Like a half-filled is already really stable, so it's not likely more will be removed. All right, so the last one here, manganese. So I hope you can see where there's 2 forms of manganese, +2 and +7. So let's just look at it. All right, to make the +2 manganese, what electrons are you going to lose? 4s. To make +7, which electrons are you going to lose? All of them, or all of the valence. So I hope you can see that. So manganese +7 does exist. It does exist. So the idea is you can lose some of your valence. You can lose all of your valence. All right. So I hope you can see why things like, silver, aluminum, zinc, why you call those fixed charge cations, because once you take away the valence, you're left with really stable subshells. Also, let's look at tin. Why can tin form a +2 and a +4 cation? Again, if you look at the electron configuration of tin, our valence electrons are these 5s2, 5p2. So to get +2 and +4, you either lose the 5p electrons. To get the +4, you lose all of the 5s and 5p electrons. So you can, just lose some or just lose all of those valence. So that's where electron configurations here for ions relates to the ideas ionization energy, how easy is it to remove an electron, and also for forming anions, how much energy do we get back when we form an anion. So that's putting it all together. Good? All right. So let's summarize all of the periodic trends here with looking at some of the properties of metals and nonmetals and some of the trends within there and relating it to ionization energy and electron affinity, things that you actually, properties you already know. I will note here that the last sections of this chapter are not learning objectives that will be assessed on the exam. They're just like, it's a bunch of random facts about elements. And that's not fun to teach. So we're not assessing that. But we will look at some trends here for metals and nonmetals. So based on the periodic table, you should know this. Where do the metals live? Where do they live? The metals on which side? The left side. The metals lived on the left side. And then the nonmetals live on the right side, yes. So looking at the periodic table, this is how metallic character, the most metal-like substances. Cesium is our most metallic substance. I would just memorize this, okay? While fluorine is our most non-metallic substance. Or you can think of it as fluorine is your least metallic element, and cesium is your least non-metallic element, right? Because they're like opposites, yeah. So I just remember cesium, most metallic, fluorine, most non-metallic. Some students are like, well, why not francium? Francium's lower. You thinking that? Anyone thought that in their head? Yeah, you did. The reason I didn't say francium, if you look real close at the periodic table, it's molar masses in brackets, meaning that it's not found in nature naturally, that it is not stable, so it just breaks down. It's like radioactive. So you'd never run into francium on the street, okay? But you could get your hands on cesium and like do stuff with it, okay? But not francium. And then students might ask, well, okay, we pointed at fluorine's the most non-metallic. Why didn't you say helium? Right, because it's more diagonal that way. Did anyone think that? Why not helium? It's because helium is a noble gas and it doesn't do anything. That's why. Okay. All right, so let's put it all together. Let's think about this. Okay, metals. Back in chapter 2, we talked about metals. They always formed the cation in an ionic compound. That's related. Forming a cation is related to what property we talked about this week? Ionization energy, removing an electron, forming cations. So if we look at those values, metals tend to have very low ionization energies. It's easy to remove an electron. So in the grand scheme of things, it's energetically favorable for metals to become cations. Okay, thinking about that. So it's easy to remove an electron. Think about metals and us understanding that like a metal sample, like if we have a metal rod, it conducts electricity. Electricity is movement of what? Electrons. Yeah, and so if electrons are moving really easily across atoms, isn't that also related to ionization energy? Energy to remove an electron. See how it all comes together here? Okay. Okay, they form cations because electrons are easily lost. All right, so that's metals. Non-metals, on the other hand, in chapter 2, we said that they were part of the anion component of our ionic compound. So they gained electrons, right? So the property that's related to forming anions is electron affinity. All right, and so the idea here is you look at the trends that non-metals typically have the most negative electron affinities, meaning that the system gets the most energy back, or releases the most energy, okay, becomes the most stable when non-metals gain electrons. So if you don't believe me that non-metals have very negative exothermic electron affinities, let's just look up here, right? Look at our non-metals. Okay, we have oxygen, fluoride, chloride. See how super negative numbers versus metals over here. Yeah, you get a little energy back if you put an electron on a metal, but not a lot, not as much as you get putting an electron on a non-metal. And so this is why this kind of mismatch of ionization energy and electron affinity of non-metals and metals is why we can make ionic compounds, where we get this transfer of electrons to form ions. And we'll talk about that in chapter 8. Okay. So let's kind of take a deeper look into metals. So here are your 1A elements, your 2A elements. Let's focus on these ionization energies here. So we see going down the group in 1A that in both of them, the ionization energy decreases. It gets easier to remove an electron. And I already have the answer up there. The reason that it decreases going down a group is because our atoms get a lot larger. N increases. So the electron that we're removing is just further away from the nucleus. So that's just applying the trend here. All right, so size because N increases as we go down a group. But let's compare 1A versus 2A elements. 1A elements have, lower electron or ionization energies than 2A elements. You can see that here, that these numbers in general are smaller than this 2A elements ionization energy. And again, the reason is size, again, that 2A elements are smaller. So those electrons live closer to the nucleus, harder to remove them. So with that in mind, okay, the idea of ionization energy, ease to remove electrons. If I tell you that adding any of these solid metals to water will cause that metal to lose an electron, what elements are most likely to react violently with water? 1A elements or 2A elements? Remember, ionization, ease to remove an electron. So if electrons are removed easily for 1A elements, they should react more with water because it's easy to remove an electron. And that's actually what we see here, that elements like lithium, sodium, potassium, they're kind of explodey in water when you put them in water, versus group 2A elements, they're not really explodey in water. You can get them to react if you add acid to it, get it to like really push it to go. But in general, 1A elements are just more reactive. And it has to do with the really low ionization energy that I could just breathe on these pieces of metal and their electrons will come off. So same thing when we put it into water. So based upon these ionization energies, which element in 1A is the most explodey in water? Which one? Cesium, yes, because it's the easiest to remove an electron off of cesium. I think there's a video of some guy, I think he's like British, and he does all of these, all right? He has like a little bit, and he throws them into like a pond or something, and I think he does, oh no, I think he got francium. I think he got francium somehow, and he threw it into like a lake, and it like blew up a bathtub or something. So yeah, look, I'll try to find it. But yes, so really low ionization energies, really reactive. I think, was it francium? I think it was francium. I think he did get it. You gotta like move quickly because it'll just decompose, right? So yeah. All right, so there we go, it gets explodey. All right, some other trends that we see here for metals, so these are metals bonded together, melting points. When you melt a metal, you break its metallic bonds that have to do with electron delocalization. That's what the bonding is in metals, and it has to do with ionization energy. So how the trend is that higher ionization energy means higher melting point, or really the trend is smaller atoms, higher melting point, because essentially the electrons are held on tighter to those atoms. So that's what we see there. And then finally, honestly, just memorize it, I guess. And this is just for metals. Lastly here, density of our metals. We know when we go down a group, mass increases according to the molar mass of our metals. We know size increases, but the idea here is that mass actually increases faster than size or volume of atoms. So we actually see density increase as we go down a group. So just, I guess, memorize that. That's all I got for you. Okay, so those are metals. Let's talk about non-metals. Metals have low ionization energies. That's what they're known for. Non-metals, on the other hand, tend to have high ionization energies and very exothermic electron affinities. But that idea, those qualities don't make for good electron transfer. So instead, when we form chemical bonds between all nonmetals, okay, when we form molecules, they bond to themselves. They share their electrons instead of transferring electrons, or instead of making a delocalized metallic bond. So in these examples, what we see here, two oxygen molecules double bonded towards one another, they're bonded to one another, where they're sharing their electrons. So we have these discrete molecules, where when we melt or boil a sample of a molecular compound, we're not breaking covalent bonds, the lines that I drew right here. So when we melt or boil something, we don't break these bonds. We don't. What we do instead is we separate these molecules from one another. Those molecules are just attracted towards one another via intermolecular forces, which we'll talk about in chapter 11, but those attractions are a lot weaker than covalent bonds. So oftentimes what I'm trying to get at is that molecular compounds have very low boiling points, low melting points, not because the bonds are weak. No, the bonds are strong, but when we melt and boil stuff, we don't break the bonds. We only move the molecules further away from one another. And those attractions are weak. So that's what I wanted to get here. All right, and so that's what you see here. Oxygen, oxygen, all nonmetals, they're bonded together. Here's sulfur atoms in a ring, all bonded together. And we'll get more into this in chapter 11. And so the big thing here is, it's composition and structure is what dictates chemical properties. And so the idea here, these substances, all nonmetals. So that gives us our covalent character and characteristics, properties that we see. And we'll expand on this in chapter 8, where we talk about Lewis structures and how to actually, figure out how do covalent bonds form versus, metals, metallic bonding, a little bit different, or versus, okay, if we combine a metal and a nonmetal, we do get electron transfer, that it is energetically favorable for that one substance to lose an electron, that other substance to gain an electron. Again, all has to do with the composition, tells us about the bonding structure that we see. Okay, so last bit here. All right, yeah, those are nonmetals. Okay. This is common trend that is asked in this section, and it's trends that have to do with metals and non-metals, okay? So it's not so much where I ask, okay, what's more non-metallic, sulfur or phosphorus? Which one's more non-metallic, sulfur or phosphorus? And you tell me what? Which one? Sulfur, yes, because it's closer to fluorine. It's closer to fluorine, that's it. So those are too easy. So we ask the questions differently. So the idea here is we can, we oftentimes interact with oxides of nonmetals and metals, so not the pure stuff. Like we rarely, or the elemental form, we rarely interact with the elemental form of these things. Instead, we're gonna focus on the oxides. So metal oxides, especially when you put them in water, are basic. So remember from chapter 4, we talked about things that were acidic. They donated, H+, versus the opposite of an acid is a base, and that donates hydroxide. So honestly, just memorize that metal oxides are basic, right? They're basic. And here's an example. Calcium oxide plus water, calcium's a metal, you get calcium hydroxide, which is a strong base. Hydroxide's in there. The trend is the more metallic the metal, the more basic the compound, more basic your solution will be. So that's the trend. More metallic oxide, more basic. On the flip side, you can think about non-metal oxides the same way, that the more non-metallic your non-metal oxide, the more acidic it will be. And so here's an example. So non-metal oxides are acidic, they produce hydroxide. So here is SO3. If you add it to water, you get H2SO4. What is that? Sulfuric acid. So here it's just a clear cut showing you that SO3 plus water gives you an acid. So non-metal oxides give you acids. And again, the trend is non-metal, more non-metallic than non-metal, more acidic. So let's look at some examples. Okay. Compare the acidity of an oxide of sulfur and an oxide of phosphorus. Which is more acidic? So I'm not straight asking you, okay, what's more metallic, what's more non-metallic? We need to kind of infer from this, okay? So if it's asking what's more acidic, what trait are we looking at? Metallic character or non-metallic character? Non-metallic, yes. So we're looking for non-metallic character. So really, this question is asking which one is more non-metallic. All right, so we have an oxide of sulfur. We don't actually need the formula, so it's just an oxide of sulfur. So I'm just going to call it SO. I don't know how many O's, so I'm going to call it SOX. And then an oxide of phosphorus. What do you think I'm going to call that? POX. Yeah. Okay. I don't know why I think that's funny. So then we locate those things on our nifty periodic table here. So we have phosphorus and sulfur. So that's where they are on the periodic table. So with all those things together, which one will be more acidic, SOX or POX? SOX, yes, because sulfur is more non-metallic. But let's check our work. So look at these oxides. So sulfur plus the sulfur oxide plus water gives us that. Here's a oxide of phosphorus. We add water, we get that. What kind of acid is H2SO4? It's a strong. How do you know it's strong? It's one of the 7. Is H3PO4 one of the 7? What kind of acid is it? Weak. Does that match what we said? Yes, it does. Oh, do you hate that? Or do you love it? Okay, all right. I won't probe you too hard. All right, so this last one. Same kind of deal here. Here it says select all the substances that will undergo a neutralization reaction with an acid such as HCl. So let me break it down for you. Neutralization reactions are between what and what? Acid and a base. So they're saying we're already reacting an acid. So we're looking for the substance that is what? The base. So we want to look for substances that are bases. So that means we're looking for oxides that have what attached to it? A metal, yes. So it's simple as that, though it's, it's the reading comprehension that we have to use here, kind of utilizing previous chapters' knowledge. So going through these. So SO3, is that an acid or a base? Why? Sulfur is a nonmetal. Yeah, so that's an acid. So MgO is a base, calcium oxide, base, and then CO2. Acid, yeah. So only those middle two will react. Probably what will happen if you did this, if you threw magnesium oxide and calcium oxide in HCl, they would dissolve. That's what would happen. They would just dissolve because they become neutralized, essentially. Okay? All right. Remember the copper cycle lab? I just thought of this. Okay? The copper cycle lab, all right, where you took, what did you take? You took copper oxide, and what did you do? You added acid, HCl, and then you dissolved it, right? You got copper 2+ and some other stuff. So I think, didn't you say that it was a neutralization reaction, right? That's like the type of reaction you said it was. Your TA probably just said, write neutralization reaction down, okay? But the idea here, now you know why it's a neutralization reaction. We have HCl, which is an acid. Copper oxide is what? A base, because copper is a metal. Oh, don't you hate that? Yeah. Okay. All right, so we're done with chapter 7. So chapter 7 homework is due Sunday. Yes. It's a short one. There's no math. There's like no math. So, okay. So let's go to chapter 8. Okay. Chapter 8, we're going to be using the same, like the same trends and ideas, ionization energy, electron affinity, kind of at the beginning here. A lot of concepts overlap. We'll be using them again in chapter 8, because now we're thinking about, okay, what requirements do we need to consider when we actually form chemical bonds? And there's a couple kind of bonds that we can describe. So in that last part of chapter 7, I described ionic bonding and covalent ionic bonding in a metal plus a nonmetal, and I talked about molecules forming covalent bonds between all nonmetals. That's what we'll be focusing on in chapters 8 and 9. Both of them are about bonding. Okay, so we're going to be talking about bonds for a long time. So this first part, we'll look at things revolving around ionic bonding. So just to remind us the type of bonds that we have: metallic bonds when all metals are present. Talked about that a little bit. Metals have low ionization energies. They conduct electricity. A metal plus a nonmetal, because of that mismatch in ionization energy and really negative exothermic electron affinity, we get full electron transfer. That an electron off of the metal gets yanked off and added to the nonmetal, and that is energetically favorable to do so. And so what we do is that, ions transfer through the transfer electrons. Ions form through transfer of electrons. Metals, low ionization energy. Nonmetals, very exothermic electron affinities. And so what we see in ionic bonding are attractions of ions. So we're going to constantly be coming back to our favorite equation, potential energy or electrostatic attractions, Q1 times Q2 over D. That's going to come up again here, because we have charged substances attracted towards one another. And then finally, covalent bonding, all nonmetals, because basically ionization energy, electron affinity are the same for all nonmetals. There's no driving force for electrons to be transferred or anything, so electrons are just shared between atoms instead. These yield really, really high energy, strong bonds, but the description here is completely different. So in your mind, we're going to focus on ionic bonding at the beginning here, and then talk about covalent bonding next week in terms of Lewis structures. So we'll probably, hopefully, get through ionic bonding. And so the idea here, the next chapters, is we want to be really focused on, okay, the composition of my sample is what dictates the structure and therefore the properties that I see, right? Because what you see here, this is composition, All right, this bonding is telling me structure. And then finally, the last chapters we'll go over will tell us properties and how, composition and structure can combine, give us different properties. All right, so Lewis structures, Lewis symbols. All right, so Lewis symbols is a way to help us predict bonding. So I'm going to highlight my tip here, all right, for drawing out Lewis dot structures for elements. We always want to dictate how many valence electrons all those atoms have, and we want to make sure that we spread out those electrons completely around the 4 quadrants. So throw out the window the idea of like s, p orbitals, okay? Just throw those out the window. Just spread out those electrons evenly throughout those 4 quadrants. This is actually a preview to hybridization that we'll talk about next chapter. So just trust me. So the idea here is, like, if you look at carbon, see how there's carbon has 4 valence electrons, but I spread out those electrons evenly. I didn't make carbon look, I didn't try to say, oh, carbon has 2 s electrons and then, p electrons in 2 different, I don't write it like that. I want to spread out those electrons. This is actually incorrect. Because what we want to showcase in these Lewis dot structures is unpaired electrons. Okay, so electrons that don't have a partner, so anything that looks like that, is capable of forming a bond, a covalent bond, versus things that have lone pairs on them. When those electrons are already paired, they typically don't participate in chemical bonding. So that's what we want to kind of focus on here, that the number of unpaired electrons in these Lewis dot structures will give us insight into how many bonds they will produce. So those valence electrons on that atom, just use the quick and dirty way to figure that out and spread out those electrons. I should note here, so Lewis symbols, okay, so Lewis, this whole chapter is dedicated to Gilbert Newton Lewis, all right? I call this chapter the Lewis chapter, because we talk about Lewis dot symbols, Lewis structures, a lot. And so when I applied to graduate school to come here to learn, to study at OSU, my personal statement, my hook, everyone needs a hook, right? It's so cheesy, was a quote by Lewis. And the quote was, Gilbert Newton Lewis once said that chemistry is the study of everything that is interesting. And I really took that to heart. I really resonate with that because I find chemistry insanely interesting. And when I, graduated from undergrad and decided to pursue a graduate degree, I wasn't done learning. I was still really curious about the world. And that's why I wanted to pursue that higher education. I didn't want to help people and become a doctor. All right, so I just wanted to learn more about electrons, all right? And so I used his quote, and it resonates with me. And so it's funny that all Gen Chem students, okay, we learn about him for like a chapter and a half, and he never won the Nobel Prize. Yeah, he never won the Nobel Prize. And we learn about this whole chapter is dedicated to him. Remember chapter 6? How many Nobel Prize winners did we talk about in chapter 6? Like 1 billion, right? Yeah, and they get all these Nobel Prizes. They only get 1 chapter, or yeah, like they're all shoved in 1 chapter. Gilbert Newton Lewis, he gets 1 chapter all to himself, and he never wins the Nobel Prize, and it's actually real controversial. Oh, it's drama, yeah. So apparently he had like enemies in the Nobel Prize committee, and it was thought that someone was suppressing his nomination. A student in my previous class, because I did the same spiel in my previous class, so sorry if you came again and you have to hear it all again. They looked it up. He was nominated 35 times and never got it. I know, and we're gonna spend all chapter talking about him, okay? So do keep that in the back of your mind, all right, and appreciate that, okay? So anyway, all right, so Lewis structures, or Lewis symbols, okay. So let's draw the Lewis symbol of selenium. So my steps here is I want to look at valence electrons. So how many valence electrons do I need to place? I don't know. 6? 6. Okay. 6 valence electrons. So I write selenium, and then the trick here is you want to spread them out. All right, it doesn't matter where you start. So 1, 2, 3, 4. Then I can start doubling them up. 5, 6. It doesn't matter where the lone ones and the paired up ones are. It doesn't matter. It doesn't matter. They could be across from each other, whatever. It's the number of the number of unpaired electrons does tell us something. Selenium, if it forms covalent bonds, is most likely to form 2 different covalent bonds because of those unpaired electrons can go on and share with other elements. Okay, next, my favorite element, Sb, which is antimony. Okay, but you didn't need to know that because you can look at the periodic table and say how many valence electrons does Sb have? 5. So we do the same thing. 1, 2, 3, 4, 5. So antimony most likely to form 3 bonds if it's in a covalent compound. All right, last question here, true or false? All group 4A atoms will have the same Lewis dot symbol. True or false? Yes. Yeah, because all 4A elements will have what number of valence electrons? 4. And again, we just spread them all out, so they all should look exactly the same. Okay, there we go. So that is Lewis dot symbols. We'll bring that back when we talk about Lewis structures. Also help us predict about ionic bonding as well. Okay, so this is the hardest part of midterm 3, is ionic bonding. It's the one part of math that we need to think about, and essentially we're applying the idea of Hess's law here, that when we form a compound, in this case an ionic compound, we don't have to go straight from reactants to products. We can think about, okay, what steps are involved to get us from reactants to products? Okay, that's Hess's law, and then we can add up all those individual steps, and that will equal the overall, reactants to products. So in this idea, we're trying to figure out, okay, what attractions are holding ionic compounds together? We call that lattice energy. All right, lattice energy. This is specific to ionic bonding because we have cations and anions attracted towards one another. Sodium chloride is composed of, like table salt is composed of sodium cations, chloride anions. They're all packed together. So the energy to separate all of those cations and anions from one another is called lattice energy. All right, and we can predict magnitudes of lattice energy based upon potential energy. We'll look at that, but I want us to numerically determine and use Hess's law to figure out what is lattice energy given some, thermodynamic quantities. So, and that's through the Born-Haber cycle. And yes, I think this is the hardest thing to teach. It's very hard for me. It might be hard for you. So I'll try my best. All right, so let's think about this. Let's try to make salt. Let's make an ionic compound. All right, so NaCl solid. If I go to a table and look up the formation value, remember that? Remember formation values? Okay, you can look up that value. That value represents the reaction, the standard enthalpy of formation for that substance. So we see that the reactants here are sodium solid, because that's sodium in the most stable state. Then we have chlorine gas, because that's chlorine in the most stable state. And we have a half. That's all right. Right? And we see here, if we do this reaction, if we throw a block of sodium into chlorine gas to make salt, like white table salt at the bottom, tons of energy is released. It's very exothermic. It's negative 400 kilojoules of energy is given off. So based upon this information, what side of the reaction is more stable? The reactants or the products? Products. Or another way to say, phrase it, which side of the reaction has stronger chemical bonds? The products or the reactants? The products. They're stronger, all right, because it's highly exothermic. What we're making is really stable, has really strong bonds holding it together. So the idea is, where does all that energy come from? It actually comes from lattice energy. All right, so let's think about the individual steps to get us there. All right, so here's the formation reaction again, but I want us to think about this. Sodium chloride, if this was chapter 1, it's made up of a sodium plus and a chloride minus, right? right? Cation and anion. But on our reactant side, do we have ions? No, they're neutral. So the idea is we can't take just neutral atoms and then like shove them together and get an ionic compound. We can't do that. We need to think about, okay, we need to turn that sodium, that neutral sodium, into a cation first. We need to turn that chlorine into an anion, then we can make the salt, all right? Because we can't go from just neutral atoms to ionic salt in one go. So let's think about the steps required to get there, all right? Okay, so let's do this. We want to basically turn that sodium solid into a cation, and we want to turn that chlorine into an anion. So I've written out the steps here, but let's do our best and predict the signs of these. Okay, so to turn sodium into a cation, what property am I talking about? To turn something into a cation, what am I doing with the electron? Removing it. So what is that? Ionization energy. So I want to use the ionization energy of sodium. But the problem is that this is sodium solid, and so a small detail is that all of those ionization energies, electron affinities, they need to be, the atom needs to be in the gas phase. So the first step is I need to turn the solid into a gas in order to use ionization energy. So that's the first step. So let's just predict, so just trust me, okay? You gotta turn the solid into a gas. What's the sign? Don't think about it too hard. What's the sign of delta H? Do I have to put energy in, or does it get released? Put energy in, yes, to turn a solid to a liquid to a gas, you gotta put energy in, so it's positive. That's a positive enthalpy. Okay. Now the sodium atom needs to lose an electron. So that's ionization energy. What's the sign of that? Also positive. All ionization energies are positive. Or you can think, oh, I'm ripping an electron from this like positive sodium nucleus, has a Z effective of positive 1. It's going to require energy to do that. Okay, so those are positive. All right, so the idea here is I'm starting with a chlorine molecule. I want a chlorine atom on the other side. So I need to break that chlorine bond. So no, like I have chlorine, I want to break that so I just have a chlorine atom on the other side. Does that require energy or release energy? Require, yes. Breaking bonds always requires energy. Okay. All right, last one. The chlorine atom, so now that we have a chlorine atom floating around in space, now that chlorine atom can gain the electron that was yanked off of sodium. That is electron affinity, right? Okay, so now let's predict the sign. What's the sign of this reaction? Negative, yes, the first electron affinity, especially for a nonmetal, is negative. It's exothermic. Okay, so if we look closely here, we have a bunch of positive signs and like one negative sign. But look, the overall reaction is really exothermic. So there's like this missing piece, this really exothermic missing piece that we haven't discussed yet. So let's think about what we just did. We turned sodium into sodium gas. We turned sodium gas into sodium plus. So that's what we have like floating around in space. We have sodium plus and an electron floating in space. We took the chlorine, we broke the chlorine in half. We took that chlorine atom and essentially combined the electron that came off of sodium to form chlorine minus. So if we think about what's floating around in our container, we have sodium plus in the gas phase, chloride minus in the gas phase, floating around. In your mind, does that look like table salt? No. In order to make it table salt, we need to bring them together. And that's the big missing piece. This bringing the ionic gas phase things together, that is lattice energy. That's related to lattice energy. Do I have that around here? I think so. Yeah, so that's the missing piece. Okay, so here's the cycle. What I want you to focus on here is the first formation reaction right there. I'm going to call it reaction 1, is written right here. That here are reactants, sodium plus half a chlorine gives us our product NaCl. That's that arrow, okay? So note how that formation value is a negative value. See how this arrow is pointing downwards? It's exothermic, goes down. Okay, so the idea is we're just gonna, instead of going straight from reactants to products, I'm just gonna take a different pathway to get to my products, right? And this is where all the steps come into play. The first step, turning the solid sodium into a gas, that's our first step after that formation step. So I'm gonna call that reaction 2 right there. You can see what's happening. We're turning that solid into a gas. That's what's happening. So see how the delta H value is positive, so it goes up. We're going up in energy. We're just taking a different route. Next, if we look closely, this is slightly out of order. If we call this reaction, ripping the sodium, the electron off of sodium, the ionization energy, we already said it's positive. That is actually described right here in this step. So if you look closely, we have a sodium neutral gas, and see how we have a sodium plus and an electron up there. And it's a positive number, the arrow goes up. All right, so that's that step right there. Okay, so this next step, I kind of skipped it. Sorry, we were kind of going in the wrong order, where we broke that chlorine-chlorine bond to get our chlorine atom. That's step 4. I'm gonna label that on this graph. It's right here. And if you look closely, if we look at this line, see how we're going from, I should do a different color. Here we go. Half a chlorine molecule, and now we just have a chlorine atom. That's the breaking of the chlorine. All right, and we only have to break half a chlorine because we just need one chlorine atom. Okay, so I've taken inventory of these reactions, and they're all right here. And we see how all of these are endothermic, so they're all positive arrows pointing upwards. So now the next step that we didn't take inventory of is step 5. I'm gonna call it step 5. This is the electron affinity. Of chlorine, we already predicted it's gonna be exothermic. So in our Born-Haber cycle here, what direction will the arrow go for this step? It's not going to go up, it's going to go down. Do we see that for the next step? Yes, we do. So here's step 5. This is the electron affinity of chlorine. And so we see we're essentially taking that electron and that chlorine. See what our product is? We have chlorine minus and sodium plus floating around in space. But is that salt? Solid salt? No. We need to bring those ions together into the solid phase. And so the missing piece is right here, all right? So this, I will do this big red thing, okay? So this missing arrow right there, that huge amount of energy we get back is lattice energy. So it's the idea we're bringing these charged particles together. They're highly attracted towards one another. We're bringing them really close in space because it's in the solid phase. All right, and we get a ton of energy back when that happens. And so that's the negative enthalpy piece that we were missing. And that's why this overall reaction is highly exothermic, because we were missing this idea. So this is actually the reverse reaction of lattice energy. Lattice energy is actually the energy to rip the ions apart, but no, it doesn't matter. It's Hess's law. If we reverse the reaction, it's the same value, it's just the sign changes. So that's the missing piece. This idea, lattice energy, is related to a lot of different things. Size of atoms and the attractions of the ions themselves, right? And that's what the next slide is. So what we see here and what's important, the learning objectives for this part of the chapter, there's basically 2. Can you numerically calculate lattice energy given thermodynamic quantities? And can you do it conceptually? Most people can do it conceptually. The math part is a little bit harder. So here, I describe lattice energy kind of conceptually. Okay, the definition is energy to rip the solid salt into ions. So it's the opposite of what you see in the Born-Haber cycle, but no matter. So it's always reported as a positive value. So ions that are highly attracted towards one another or really close are going to have really high lattice energies. So this just follows our potential energy equation, all right? That Q1 times Q2 over D. Essentially what we see here, if we look at this table, is that lattice energy increases when charge increases of our ions. Lattice energy also increases when size of ions decrease. So if we kind of look at these here, all right, I'll zoom out so you can get those things. So what we see here, this first column, we have all our compounds are +1, -1, right? these all have relatively low lattice energies, like sub 1,000, versus like these substances, all right, are like +2, -1. These two are +2, -2, and then scantium nitride is +3, -3. So you can see as the magnitude of the charges increases, right, as the strength of your magnets increase, don't you feel more attraction? So it's more energy to separate them. So that's where charge comes into play. So we want to look at Q1, Q2. And then the other trend is with size. We look at size when we're within the same Q1, Q2. So we'll pick back up after here. On next week, we'll look at some numerical values of calculating lattice energy and then do some examples with the conceptual ones.